Hi everyone and welcome. So today we're going to be talking about the last of our topics related to Laplace transforms. We're going to talk about the Dirac delta function. You notice I put function in quotation marks for reasons that will become clear shortly. So strap in folks, it's about to get weird. But the Dirac delta function is super important. It's just a little bit different than the kinds of things you might have seen before. So let's get right into it. The final piece of the puzzle for differential equations and Laplace transforms is the thing called an impulse response. The idea is this. What would happen if we apply a lot of a force very quickly, instantaneously? So the force is applied all at once in one instance, and then it's done. No more force being applied. So this is something that's very short duration, but large amplitude. For a spring system, this would represent that you have a spring that can move on its own, but you're applying short, very forceful, instantaneous force. For an electrical system, which is also modeled by the spring equations, this could be something like being struck by lightning. Suddenly, there's a ton of voltage in the system, and then it's done, right? It's not coming in anymore, but that can leave a lasting effect on the way the system behaves. And for a model of infection, like in my work, this could represent the injection of medicine. Suddenly, in no time at all, you have medicine in the system that wasn't there before. And how will that affect the culture of the virus and other cells that are involved? So we'd like to understand this kind of system if we can. And we're going to start to understand it by doing an approximation. Right, so an approximate impulse function would be one like this. We're going to start with a function that has an area of 1 under the curve, but it's only non-zero for a very short interval of time. So that's represented by this function p sub epsilon. It's going to be equal to 1 over epsilon on the interval from 0 to epsilon. It's going to be 0 otherwise. So graphically, this function would look like, well, from 0 to epsilon, it will be 1 over epsilon, so that the area under the curve is 1, and then it's 0 everywhere else, right? Now, if you make epsilon much smaller, if that's your epsilon, then 1 over epsilon will have to be correspondingly much higher. Right? It still has an area of 1 underneath that curve. And now you can imagine what happens as you squeeze further and further in this direction, get closer and closer to 0, you're going to get a very tall spike. So the force applied per unit of time is very high, but the total amount underneath that curve is always the same. All right, so that illustration makes it a little bit hard to see. So let's get rid of the top end here. We have a function like this. Okay, so what are we doing with this? Well, what happens as epsilon starts to get closer and closer to 0? That's a little bit of a complicated question. As a pointwise limit, so if you look at what happens at any individual point along the x-axis, eventually epsilon gets below it and the value of the function is 0. So the function is 0 for the limit of this function is 0 for every point except t. At t equals 0. At t equals 0, it keeps getting higher and higher and higher, so the limit goes to infinity. In fact, the limit doesn't exist. So that's the first hint about why I put function in quotation marks. This thing right here, 0 everywhere except infinity at 0, that's not a function. That's just not a function. Function has to have a value at every point. And if it were a function, if we had to think about what kind of function are we talking about here, this is basically the 0 function. It's 0 almost everywhere. It's 0 everywhere except at the point 0. So a little bit of an unusual thing to call a function. Now, what about a useful way of thinking about this also is in terms of integrals, right? So if we have an integral, what happens when epsilon is very small is, well, f of t will be approximately equal to f of 0 for 0 to t, for t between 0 and epsilon, right? The idea is that for very small time intervals, you have a continuous function, so the value does not change very much. So what happens if we try to integrate f of t a function f of t, against this approximate impulse function that we've just been building? Well, the integral from negative infinity to infinity will be 0 almost everywhere, because this function p is 0 almost everywhere, except between 0 and epsilon. In that region, you're going to have the function equal, p epsilon is going to be equal to 1 over epsilon, so we get this guy. But since that's such a short interval, f of t is approximately equal to f of 0, and so we can pull that out, pull out the epsilon, integrate. That's just the area under 1 between 0 and epsilon. That's epsilon, and so in the end we get that this is equal to f of 0. So by integrating against p of epsilon, what we've done approximately is picked out the value of f of 0. And as epsilon goes to 0, this becomes an equality. So this approximate here becomes equal, and the integral of f of t against the limit function, which isn't really a function, is that integral is always going to be just equal to the value of f at 0. So in the limit, we have a function that's 0 everywhere except at t equals 0. It's infinity there. And when we integrate f of t against it, which is what we call it when we multiply by something and then integrate, the integral is equal to the value of the function at 0. I got bad news for you, folks. There is no function like this. That's just not a function. But someone came up with the idea of what are called generalized functions. And this impulse is the first example of one. The limit function of p epsilon of t is what's called the Dirac delta function, denoted delta of t. It's part of a wider branch of mathematics that's called real analysis, which you'll be introduced to if you haven't been already in Math 331. And more specifically, this is what's called distribution theory. This function is a distribution. It's part of distribution theory or measure theory. All of that is even beyond Math 331. So you're seeing something pretty special here, something a little bit unusual, this Dirac delta function. But it has uses in physics, so we want to be able to work with this guy. All right, so let's review. How can we think about delta of t, this Dirac delta function? We're just going to call it a function now. I'm not going to have to say the quotation marks every time. But what do we think about it? Well, for one thing, it is definitely weird, right? Its main property, this is the one that we've just seen, its main property is that the integral of any function multiplied by the delta function is just going to be equal to f of 0. Just picks out that one value of the function. That normally doesn't happen. Normally, integration is about smoothing something out and computing an area, but it's not computing an area, it's just finding a value. So similarly, if we shift the delta function, if we have delta of t minus a, we integrate against that, we get f of a. So we can pick out any value we want in this way. So in fact, anytime you integrate over any interval with the delta function, you get either, sorry, there's a slight error here. You get either 0 or you get f of c. So if c is in your interval, you pick out f of c just like we did up above. But if c is not in your interval, then the result is 0 because everything's 0 all the time. Okay, so the function is 0 everywhere except at a single point, but the area under the curve of this one point is 1. It's outrageous. It just shouldn't be, but it is. It's a thing. It's a thing that we have to get used to. So how do we know that? Well, the integral from negative infinity to infinity of delta, so the area under its curve, well, it's just 1 times delta. And of course, that just means that we pick out the value of this function at 0. It's the function 1, so we get 1. So this isn't, this is a weird function. It's a function that clearly has no area under the curve, and yet the area under the curve is 1. All right. If we want a heavier function, more force, we just multiply by some constant to increase the area under the curve. So you can have 4 delta, and its area under the curve will be 4, right? That kind of thing. So in a very real sense also, this delta function is the derivative of the Heaviside function. What was the Heaviside function? Remember, that's the unit step function. Let's shift that over a little bit. The unit step function, right, that goes like this. It goes 0, and then it jumps up to 1. Now, clearly, this function is not differentiable here. But if it were differentiable, then what would the derivative look like? Well, it would have to be 0 before, and the derivative would also have to be 0 afterwards. And then something has to happen to jump the function up 1 unit in integral, right, in that space, right? So in some sense, the slope here should be infinite. The slope doesn't exist, but if it did, it should be infinite. And so in a very real sense, the Heaviside function, you take its derivative, you get the delta function. Another way of putting it, the antiderivative of the delta function is h of t, because if we integrate from negative infinity to t, right, so that's a function, delta of s ds, it's going to be 0 all the way up to 0, and then after that, it's going to be equal to 1, just like in this calculation that we did up here. So what's the function that's 0 and then 1? That's the Heaviside function. So what's the moral of the story so far? Well, the moral of the story so far is, my friends, there is a lot of weird mathematics out there. It's crazy. It's a big, crazy world of super cool mathematics. And it is cool. It is really interesting stuff. It's out there, and it's ready to bend your mind. I hope you take the time to explore some of it. And don't get too discouraged that it's weird. The weirdness is the thing that's cool, right? You have the tools for understanding these things that a lot of people have no chance of understanding. And I'm hoping that this Dirac delta function will become part of that world in your minds. So let's use this. Of course, at this point, you must be asking yourself, does the Dirac delta function have a Laplace transform? Of course you would ask that. And of course it does have a Laplace transform. What is it? Well, let's see. Just have to follow the definitions. Thankfully, the Laplace transform is defined in terms of integrals, and delta functions work really great with integrals. So all we need to do is take the definition, integral from negative infinity to infinity, delta of t minus a times e to the minus st dt. That's how, this is the shifted delta function. So if we want the standard one, we let a equals 0. If we do that, remember, all that we do when we integrate against the delta function is we plug in whatever value is here into this function, and that's the value of the integral. So we get e to the minus sa. In the special case where a equals 0, we get that the Laplace transform of the standard delta function is just 1, right? Which fits in with some of the craziness from before, because remember, the Laplace transform of the Heaviside function is 1 over s. And we said before that this is kind of like the derivative of that. And we have a formula for finding the Laplace transform of a derivative. The Laplace transform of delta t should be the Laplace transform of the derivative of h of t, which is, again, not a thing that exists, but go with me on this. Our formula says that that's s times the function itself minus its value at 0. So that's s times 1 over s minus 1, which is 1. So awesome, it works. We get the right derivative, or the right Laplace transform, by thinking of the delta function as the derivative of the Heaviside function. It just works. It just works, my friends. Okay, so let's use this in the context that we usually want to use these things. Let's put it into a differential equation. So remember, the delta function represents a sudden change. Let's see how this works in practice. So here we have a spring system. Y prime prime plus 2y prime plus 2y equals delta of t minus 1. So we have a spring. If we do a little bit of analysis on this, you'll see that this is an underdamped spring. And then we have this impulse function. We're going to add force to it, a force of magnitude 1 at time t equals 1. Right, so the t minus 1 makes that happen at 1. But before that, the initial conditions for this system are just 0. So the system is going to be at rest. So the spring shouldn't do anything for a while until this force rolls around and changes things. But let's approach this using Laplace transforms. We're just going to take the Laplace transform of both sides of this equation. Right, so we get the Laplace transform of y prime prime plus 2y prime plus 2y equals the Laplace transform of delta of t minus 1. Right? And we know how to do all of these things. This is s squared y of s minus s y of 0 minus y prime of 0 plus 2 times s y of s minus y of 0 plus 2 y of s equals, and our Laplace transform for this guy is e to the minus s. Okay, so all of these things here are 0, 0, and 0. And so getting our y of s's together and factoring, we get s squared plus 2s plus 2 y of s equals e to the minus s. So y of s is equal to e to the minus s over s squared plus 2s plus 2. Now, using completing the square, we can rewrite this as s plus 1 squared plus 1. All right, so now we need to find the inverse Laplace transform of this guy. Y of t will be equal to the inverse Laplace transform of e to the minus s. Well, let's rewrite this in a slight way. E to the minus s times 1 over s plus 1 squared plus 1. All right. Now, we have to recall a rule. So we had a rule at some point about what happens when you have the Laplace transform of a shifted thing. So one way that we might remember this is that the inverse Laplace transform of e to the minus alpha s, f of s, is equal to h of t minus alpha times f of t minus alpha. Or another way of putting that would be, this is h of t minus alpha times the inverse Laplace transform of f of s, but with t minus alpha plugged in. So we're going to apply that here. We have this multiplying by some exponential. That means that we're going to be shifting the Laplace transform of this thing, whatever it happens to be. So let's take that with us over to a new page. Good. All right, so this is what we were working with before. So what is that going to be equal to? Well, so to take care of this e to the minus s, we're going to bring that out, and this is equal to, well, we're going to be multiplying by h of t minus 1, because this is e to the minus 1s. And then it's going to be the inverse Laplace transform of 1 over s plus 1 squared plus 1, but plugging in t minus 1. All right, so let me clean up my 1 there. It looks ugly. Okay, so what is the inverse Laplace transform of 1 over s plus 1 squared plus 1? So if we consult our table, so we could use the shift theorem here again to take care of that s plus 1, or if we consult our table, we'll see that this is, so we've still got our h of t plus t minus 1. And this will be, well, how do we want to say this? Let's say it this way. The inverse Laplace transform of 1 over s plus 1 squared plus 1 is equal to e to the minus t sine t. Our formula says now all we have to do to get our final result is take that and plug in t minus 1. So it will be e to the minus t minus 1 sine of t minus 1. So what is this thing? Well, what this is, the Heaviside function here, h of t minus 1, will be 0 up until 1. And then after that, this whole thing, right, everything, this is all just shifted. This is just shifted version. Shifted e to the minus t sine t. right? So our graph will look like this. So there's 1. And we continue after that. Our graph will look like 0 up until 1. And then after that, it looks like e to the minus t sine t. So it will look something like this. Right? So what is described? We have a spring system that was doing nothing, right? It was doing nothing at all. That's what's going on here. It's just sitting at rest. At time 1, bang, something happens. A force is applied, a force of magnitude 1 all at once. And then the force is done, and the system has to react to it. And what it does is it starts moving, and the damping takes over, and it dampens down to 0 again. Right? That's the effect of a delta impulse at time 1. All right, let's try one more example of this thing, because, again, it's a bit strange. And let's see if this helps clarify things at all. This time, the system's a little bit different. Not a spring anymore. In this case, we're just going to have y double prime equals some forces. So acceleration determined by, we're going to be applying some kind of acceleration with a magnitude of 1 at time 1. And then minus that, we're going to do in the opposite direction at time 3. So let's, again, just use our Laplace transforms to see what we can do. See what happens. So we apply the Laplace transform to this. We have y prime prime. And then on the other side, delta of t minus 1 and delta of t minus 3. All right, so s squared y of s. The other stuff is 0 because the initial conditions are 0, equals e to the minus s minus e to the minus 3s. And so y of s is equal to e to the minus s over s squared minus e to the minus 3s over s squared. And again, we take the inverse Laplace transform. This will be the inverse Laplace transform of e to the minus s over s squared minus the inverse Laplace transform of e to the minus 3s over s squared. All right, using our trick from last time, this will be h of t minus 1 times the inverse Laplace transform of 1 over s squared, but plugging in t minus 1, minus h of t minus 3 times the inverse Laplace transform, again, of 1 over s squared, this time plugging in t minus 3. And what is the inverse Laplace transform of 1 over s squared? Well, it's just equal to t. And so we just need to plug in t minus 1 and t minus 3. So we get the following thing. Y of t equals h of t minus 1 times t minus 1 minus h of t minus 3 times t minus 3. Okay, that's our solution. What does it mean? Well, again, Heaviside functions and the way that they work, Dirac delta functions and the way that they work, it can all be a little bit hard to see what's going on. So bringing that guy over, let's see what we can do. Get rid of that guy first of all. Okay, so what is this function? Well, just reading off the Heaviside functions, first from 0 to 1, nothing's going to happen. This is 0. This is also 0. So from 0 to 1, the whole function is equal to 0. So it's going to be 0 for 0 less than or equal to t less than 1. Then between 1 and 3, only the first term is going to be 1 here, and then the rest is 0 over here. So it's going to be equal to t minus 1 for 1 less than or equal to t less than or equal to 3. And then from 3 onward, both of these things are going to be on. So it's going to be, you're going to have the t minus 1, and you're also going to have minus the t minus 3. So what does that equal to? That all equals to 2. So we get 2 for t greater than or equal to 3. That's the that's the solution to this differential equation. A little bit of a strange solution. It's piecewise defined. Some weird things are going on. What does it look like? Well, let's graph this guy out. So this is 1, 2, 3. So it says that from t equals 0 to 1, nothing's going on. And then at that point, we have the first impulse, right? So as I've been saying, bang, something happens. It's an impulse, a positive impulse. So things start moving. You have acceleration in the positive direction. This thing starts going. So its position goes up. We have t minus 1 that goes through this point, goes up at slope 1, goes like this. All right, so the object starts moving in a linear path in that direction. Right? The acceleration has all been applied at one time. It gets some velocity, it starts moving in that way. Right? So again, acceleration impulse is delta. That means the velocity was Heaviside. It was 0, and then it was 1. Right? And we see that in the slopes, 0 and then 1. And then at time 3, bang again. Something happens, another impulse. Now in the other direction, so suddenly a bunch of acceleration is imparted in the opposite direction, and it cancels out the acceleration that happened before. The velocity is brought back down to 0, and the object stays at 2 after that. All right, so that's Dirac.